Hey everybody, how's it going? Mr. Tannen here. I was gonna make a quick video slash also at the same time actually make the answer key here so I can post it as a PDF, but also for people who wanted to see the video explanation. If you wanted to at this time start playing the video at 1.5 or double speed, feel free. I often like to do that. So the first question was to use the following table of values to compute the derivative of f of g of x at the value x equals 2. So right away, this is actually the way we define the chain rule. So these problems are also asking about the chain rule. So what we're going to need to do is take the derivative with respect to the interior and multiply that by the derivative of the interior and evaluate that at x equals 2. Running a little low on space. Let me make my pen a little finer here. So now I'll just put in I'll plug in 2 for x so that I'll be prepared to now use my table to solve. So let's take a look. Well, I can start on the inside. G of 2, when x is 2, is 3. Okay, so I got f prime of 3. G prime of 2 is 2. Now I have f prime of 3 times 2, and f prime of 3 is 2, so I get 2 times 2, so this is 4. So this equals 4. Not too bad. Nice to have that chart there. Let me switch to green for my next problem. Oh, yes. So, interesting. Remember, another way to write this, which is sometimes helpful when we have the chain rule happening, is cos squared of 3x is the cos of 3x squared. So first, I'm going to differentiate this with respect to the to the interior, excuse me. So it'll be 2 times the cos of 3x all to the first, or just cos of 3x. Now I need to differentiate the interior of this. Well, there's a cos of 3x in there, so I need to take the derivative. The derivative of cosine is negative sine with respect to the same interior, but now I have another function in here, so this is a double chain rule, and the derivative of 3x is 3. So 2 times 3 is 6. This gives me a negative 6 sine of 3x cos of 3x. Would indeed just give me negative 6 cos of 3x times sine of 3x, and we could leave it as that. Sorry, I was having some issues with my drawing tablet running low on batteries. Alright, so this was the one where we had the tortoise hiding a treasure trove of helpful hints. That tortoise certainly looks sleepy. I mean, these tortoises can live hundreds of years, right? Over 100 years. A long, beautiful life. So, find all the points of the graph of y equals cos squared of x where the tangent lines are parallel to the line y equals negative x. So these hints were basically some things that I think were good reminders for myself. One, you could solve this graphically or algebraically, but as we saw with the one we did together in class, you'll need this trig identity to change from 2 trig functions being multiplied to a single trig function. Of course, maybe this hint could have come first, the blue hint, that the strategy is to set the derivative equal to the slope of the line that it's got to be parallel to, and then find the x values that satisfy the equation. And the last hint is about the answer format, because these are periodic functions, there's not just one spot where this graph will be parallel to this. There's actually an infinite number of spots. Depending, I guess this was a little funky here, but k is any integer, pi would end up being, I think, the period, which ends up being the period of this one. And even though I know most functions, we talk about having a period of 2 pi, so this could be a little confusing, but for this one, we do have this notation here. So first, let's find the derivative. So we want to take the derivative of cos squared of x and set that equal to the slope of here, -1, and then solve. So this is the same as cos of x squared. So we get 2 times cos of x with respect to the interior times the derivative of that is negative sine of x equals -1. Okay, check it out. -2 sine of x cos of x equals -1. Multiply both sides by a negative. I would get 2 sine of x cos of x equals 1. And if we look up here, this is where we could use this trig identity, because it would be hard for us to solve this as is, but we know that 2 sine of x cos of x is actually the same as sine of 2x. So what that means is we could actually take the arc sine of both sides, so it would end up being the arc sine, well, the arc sine on the left side just undoes this, and we would, right, these undo one another. We get 2x equals the arc sine of 1. It's basically saying what radian measurement has a sine of 1. So this is a function that we use our calculator for. So I go to sine. I'm going to pop open this mamma jamma here, and I would say, okay. Oh, look at some funky graphs happening. Nice. So I hit second sine and then a 1. Let me confirm my calculator's in radians. Yes, it is. Hit enter. Bam. Oh my gosh, what am I talking about? Of course it's pi over 2. I didn't even stop and think. Too reliant on technology. What? I mean, yeah. What angle has a sine value of 1? Well, 90 degrees, right? Pi over 2 on my unit circle. Bada bing, bada boom. At 0.01. Oh, man. So when I divide both sides by 2 or multiply both sides by 1/2, I get pi over 4. But because this function's period, you can see the sine of 2x, right? The period's it has a horizontal shrink by a by a factor of 1/2. So rather, the period is actually going to be pi. So that's why we would have to say it's going to be x equals pi over 4 plus pi k, where k is any integer. And if I go to my graph, this could be a fun one to see on Desmos. Pull it up. What we'll see here is that when we put in our original functions, cos squared of x, and we could put in our y equals -x also. And then let's make our x go by pi and Well, we can now see that at pi over 4 right here is the one spot where it gets parallel to this, right? Right there. But then if we add another pi to it at 5 pi over 4, again, and then again at 9 pi over 4. And if we add a negative integer, right, negative 3 pi over 4, negative 7 pi over 4, all those spots, it just for an instant there, when it's at its steepest, right there, has a parallel slope to this one. And we can use calculus to find those points. This derivative is quite powerful and elegant and beautiful. Much love, everybody, and thank you.